Okay, so going over homework from 4.4, we were supposed to sketch the graph of each factored polynomial. So if it's already factored, we know a lot of stuff. Bless you. We know that this is a 0, so x equals 0. This is a 0, so -2, opposite math. And this is a 0 twice, so +1. And because it's a 0 twice, it's going to bounce. We call that a multiplicity of 2. So if this is 2 or 4 or 6 or an even number, it's going to bounce there. And I need that to happen because this has 1, 2, 3, 4 zeros. That means it's a degree 4, which should have either this behavior where it goes up or this behavior where it goes down. Which of these two is it? It's going to go down because of this minus. So we've got the zeros. We can count out the degree, and the minus tells us it goes down, so it should look like this. But how does that work with our bouncing stuff? So we've got a 0 at 0, which for whatever reason, I don't know why, but that seems hard for some people to set this one equal to 0. So you set each one that's being multiplied equal to 0, including just x. So x equals 0, and then -2, and then +1, and my end behavior is going down on the ends, so end behavior. So we can get all of that just from it being factored, which this is my favorite way to write polynomials for graphs because it's got all the data I need without me having to like do synthetic division and find the zeros. So now I need to think about all of these things. At +1, because of this 2, it's going to bounce, meaning it's going to go up and then back down. But then everything else, it's going to go through here at -2 and through at 0. So it's going to go through at -2, and it's going to come back up to 0 and go through, and then they're going to meet. So it still has a sort of W-looking behavior. It's just not equal. Like these aren't the same height because one of them bounced. And this is my sketch for 3. Good? Okay. 7 says f of x equals x minus 4, 1. There's one of them, x plus 2. There's 2 of those, so that's 3 altogether. And then x minus 3, there's 3 of those, that makes 6. It's not x equals. This is going to be x to the 6. So even in behavior. But this one's going to go up because I don't have, like this one had a minus and this one does not. So this is going to go up on the ends and have some wiggles in the middle and then go up. And I could have this many wiggles or I could have less. But I just know that the end behavior is like this. And we have +4, 1, 2, 3, 4. That's this one. -2. It's going to bounce here, right? This one's going to bounce because it's squared. And then at +3, it's going to go through. So end behavior goes up. So I go to the ends and I actually make it go up. That's my end behavior. And then I think about bouncing at -2. So I'm going to go ahead and do that one so I don't forget. And then it's going to go through, and meet this one. And again, I don't know how high this goes. It could have gone up really high. In fact, well, I'm not going to do that because it's not a polynomial, but it could have gone like this, and it could have gone down, except it wouldn't cross back. It would just be skinnier. I don't know exactly how high it goes, but I just know it has this general shape where it goes up on the ends and has these 3 zeros. Okay? Okay. And then what was our last one? 37. 37. Okay. So 37 gave you different information. 37 says, hey, find for me the polynomial, not the factored version, but the polynomial that has degree 3, only real coefficients, so no imaginary numbers, x equals -1 and 5 plus I. Y-intercept equals -52. All right, so this has some bigger concepts to it because this came from the quadratic formula. Because this says degree 3, but you only see 2 zeros here, right? This is one of them, and this is the other one, right? Okay. So first thing I want you to recognize is that if you use the quadratic formula to come up with this answer, the quadratic formula would have said 5 plus or minus the square root of -1. That's the only way the quadratic formula works. And it would have said like over 1 if it was simplified. So every time you see an I or a square root of 2 or 7 or whatever, anytime you have something right here that says plus, or even if it says minus, you need to find the conjugate of it. You can't have one without the other. This is the only way the quadratic formula works. So if they tell me 5 plus I have to include 5 minus I. So that's a rule. You're just going to have to memorize it. You need the conjugate pair. Now I have 3 zeros. 1, 2, 3. So for me, there's 2 things I want you to be able to do. Number 1, actually 3 things. Number 1, I want you to be able to recognize that if you have the plus version, you need the evil twin. These are twins. This is the one that looks just like this one, except it has an opposite sign. Then second, I want you to be able to write it in factored form. The form before it's a polynomial. And that looks like x. Do I put +1 or -1 in my factor for this? +1. This one's harder. So it's always x minus when we write it out. So I have to write x minus this whole thing. I have to take whatever the 0 is, even if it's complicated, and write x minus the 0. And then the one we made up on our own, we came up with because we know the rule that says they're always in pairs. And we have to go x minus and then put 5 minus I. So this I want you to be able to do without question. I want you to notice that these are evil twins and come together. They're called conjugates. I've used that word a lot. I bring it up every time we have this kind of thing. And then I definitely want you to be able to write it in factored form. For some problems, I want you to be able to multiply it out, and I'm going to multiply this one out for you. The book wanted you to multiply this one out. Sometimes I would just ask you for factored form. So did you get this as factored form? Okay. This is going to be your favorite because then you're done. But if you want to multiply it out, you want to do these 2 first. So I'm going to multiply these 2 first, and then we're going to multiply by x plus 1. So I have to do this. Let's write it pretty. X minus 5 minus I. X minus, and then both of these are minus. And then x minus 5 plus I. So I'm going to rewrite that all by itself so that I can multiply. We did three-digit multiplication with polynomials before. It's a long distribution. So x times everything, -5 times everything, and -I times everything. So what happens is cool because things cancel. X times x is x squared. X times -5, -5x. X times I is positive xi. So x is done. -5 times x is -5x. Oopsies, there. And I'm going to line things up that match. -5 times -5 is 25. I'm going to put it over here. I don't have a column for that yet. And then -5 times I is -5i. I didn't have a column for that either, so it doesn't have an x. How am I doing so far? Okay, now I times everything. -I times x goes here. -ix or xi, it doesn't matter, they cancel. Negative I times 5, they're both negative, so positive 5I, they cancel. Negative I times positive I is negative I squared, and I'm putting it with the 25 because how much is I squared? Exactly. Good job. So this one's negative 1. This is negative negative 1, which is plus 1. So now I have, not enough paper, I have x squared minus 10x, because these two together, that canceled. This is 26. Okay, there we go. And now I have to multiply again times x plus 1. So it's a long process. Do I want you to do it every time? No. Do I want you to understand that it's only a polynomial if you multiply it out? Yes. I probably wouldn't have you do it on one this long, but I might have you do it on something that wasn't this long. But I definitely could ask you to put it in factored form because you're just writing it out. Okay? I'm going to finish this out though. This is the same that I just did. I'm going to multiply x times 3 things and then 1 times 3 things. So that's going to be x cubed minus 10x squared plus 26x plus x squared minus 10x plus 26. So that's x cubed minus 9x squared, because these two together. 26 minus 10 is 16x plus 26. So this is the polynomial. Note how all the i's canceled. It looks like a regular polynomial, but it's only going to cross the x-axis at -1. These are imaginary roots that make it have a squiggle to it, but they don't cross the x-axis. So they would be like, it would cross at -1 and then do something like that, where it doesn't cross the x-axis again. But it does affect the graph and make it not straight. 37. I just gave you one of those because I wanted you to try it, and then we're going to do some more of that tonight. Let's do one more like that right now. Okay, so let's do write it out as factored form only, not multiplied out, but factored form. What is the factored form for a polynomial with zeros? X equals 2, the square root of 3, and 6i? Question mark. So take a second, see if you could write out the factored form, just the factors, not the multiplying it out, and consider if any of them need their evil twin. And if you can spot what rule that is, where you would need the evil twin or not. How many zeros will we have? Right now I have 3, but that's not right. How many should I really have? Does 2 need an evil twin? Is it something that would look like it would come out of the quadratic formula? Okay, so regular numbers don't have to come out of the quadratic formula. But anything that would be like, if you had x plus 9, x squared plus 9, if that was a factor and you solve that and set it equal to 0, you'd have x squared equals -9. When we take the square root of that and the square root of that and put plus or minus, see that looks like the quadratic formula with a plus or minus, you'd have x equals plus or minus 3i. Okay, so anytime you have a square root, even if this had said x squared equals 7, you'd have the square root plus or minus, you'd have x equals plus or minus square root of 7. So if it's a square root that you can't simplify, then it definitely has to have its evil twin either from this or from the quadratic formula. So 2 is just a regular factor. Like it would go in. It doesn't need -2 to work. But this one, would you use either this form or the quadratic formula? Yes. You need the square root of 3 and you need what? You need to have plus or minus. So you could put it in the front like that if you want. Or you could say, I need 3 and -3. 6i would be the same. It would just be like this one. So you need plus or minus 6i. So if it has a square root or an I, it has to have the plus or minus. So the factored form would be x minus 2, x minus the square root of 3, x plus the square root of 3, x minus 6, it doesn't matter the order, but I'm just trying to keep it the same, x minus 6i and x plus 6i. And that would be done. So what do you need conjugates for? Conjugates are for radicals or imaginary numbers. Or something like 2 plus or minus the square root of 3. You need the plus or minus in between the two numbers. So it can be simple, like these two guys, or it can be a binomial, and you have to have the plus or minus because there's a square root there. Okay, so I've got 3 problems that you're going to try along those lines tonight. The one thing that they say in the new problems that we have for practicing tonight is it says you have zeros. So this is example 2. Zeros are x equals 1 with a multiplicity of 2. The only other zero is x equals 5. The degree is 5. Do you think you could write that in factored form? So tonight's homework is just writing it in factored form. See if you can understand what that's saying. X equals 1 with a multiplicity of 2. The only other zero is x equals 5. The degree is 5. So what are the two zeros? How do I write those as factors? For this one? X minus 1. And then the other one is x minus 5. 1 has a multiplicity of 2, so we put a 2 there. Or we could write x minus 1 times x minus 1. We write 2 of them. How many does the x minus 5 have to have? The total degree is 5. Like the degree of the whole thing. The degree of, they would have written out more words. They would have been better writing than me. The degree of the polynomial is 5. So when it's multiplicity, it defines one thing. I'm saying the degree of the whole thing is 5. And I wrote my problem. I didn't give you enough information. I think it's better now, and that's 5. Okay. So sometimes you could apply other stuff. What if they said the leading coefficient was 2? Where do we put a 2? Yeah. Because we'd say x times x times x times x times x times 2. It makes it 2x to the 5th. Okay, so you have a couple problems like that for tonight. Then let's look further and see where we are. But real quick, I want to talk about the domain of rational functions, and we'll do 4.5 tomorrow with some theory on number sense tomorrow. But rational functions, do you remember rational comes from ratio, comparing a number to another number like a fraction. So rational functions would be something like f of x equals x squared minus 4 over x minus 2. This is a rational function because it's got a top compared to a bottom. But I just want to talk about domain right now. There are 2 domain breakers. This has potential for one of them. what can x not be? What would break this function and put 0 in the bottom? Because it's not 0. What would put 0 in the bottom? If you substitute any number in, you can put in 5, because 5 minus 2 is 3. You could put in 7. 7 minus 2 is 5. You could put any number here except for what? Nope, 0 minus 2 is negative 2. That's cool. What can you not put here that would make 0 when you figured it out? 4 minus 2 is 2. We can't have x minus 2 equals 0, so how much is x? 2. No, it just can't be 2, period. That's it. 2. If you put 2 in here, you get 0. It can be anything but 2. So when you write the domain for something like this, you can just write it as simply as that. X cannot be 2. It can be 5. It could be 7. It could be 1,000,000. It just can't be 2. And so we're going to talk about how that works. But I need for that idea to make sense from the beginning, because it's going to have a lot to do with what we do going forward. Now, let's try that again. So let's say g of x equals x plus 4, and then, and then over, let's do x squared plus 5x plus 6. So just the domain. X can be anything. It can even be negative 4, because it's okay to have 0 on the top. It's okay to be 0 on the top. You just can't be 0 on the bottom. Okay? That's no. That's what we're trying to fix, is where would this function not be graphed? Where would there not be a value if we plugged it in? So what we do is we try to figure out what would be 0. You take it aside, x squared plus 5x plus 6, and you set it equal to 0, or you could say it's not equal to 0, that's fine. And then you'd have to factor it. It's a trinomial, so we're going to do 2 sets of factors. What are factors of 6 that add up to 5? 2 and 3, right? X plus 2 and x plus 3. They make 6 when you multiply, and they make 5 when you add them. So x cannot be 2. Oops, negative 2. And x cannot be negative 3. Because if you plug that in, negative 2 squared plus 5 times negative 2 plus 6, that would be 4 minus 10 plus 6. That's 0, right? So it's not allowed. You couldn't have negative 2. It would make 0 in the bottom. So what we know is if we were going to make some big elaborate XY chart, we wouldn't put negative 2 and 3 in there. Because if we put them in, it breaks the function. So that's what we're looking in, is what numbers can go here. And they could be anything except for negative 2 and negative 3. There's one other big idea I want to talk about before we actually make notes for this section, and that's this. Okay, when you think about a big number over a little number in a fraction, and I'm talking about any sort of concept. Let's say our big number is 7 and our little number is 1. This is a big number, right? Not like 0. This is 7. How about a big number like 7 over a smaller number like 1/2? What happens? We get 14. It gets bigger, right? So the littler the number is on the bottom, when you flip it over, this is 14. How about 7 over 0.01? 700. So the smaller the number on the bottom, the bigger the number is in total. It's kind of an interesting concept. So big numbers over little numbers are actually big. Because when you divide and flip that number over, it makes it larger. don't know. But let's think about the opposite. Let's do a little number over a big number. Let's switch it. So 1/7. We can imagine a piece of pizza that has 7 slices. That would be a really awkward way to slice a pizza, but we can imagine taking one slice of it, and we could see it. It would be a regular number that we could figure out, 1/7. How about, so that's just 1/7. How about 1 over a bigger number, like 700? What would that be? I don't know either. So let's just look at a calculator. So let's say we have 1 divided by 700. 0.0014. This is a very small number. It's like close to 0. Right? I can't divide my pizza into 700 slices. You know, that's nothing. What if I make the number on the bottom even bigger? So 1 over 70,000. 1 divided by 70, 1, 2, 3. You can. But the calculator isn't so clear here. Why is that? Look really closely at the calculator. It says 1.4 times e to the negative fifth. Oh, yeah. So they really mean, here's the decimal, 1, 2, 3, 4, 5. There we go. So even closer to 0, right? That's just what you said, count the zeros. Exactly what you said. So when you have a little number over a really big number, the bigger the number gets on the bottom, this approaches 0. How would we describe this one if this one approaches 0? What's the opposite of getting smaller? What's the biggest number you can think of? Or biggest mathematical number you can think of? It's not even a number, mathematical concept. Big? Really big? Really big? Infinity, yeah. So the smaller the number gets, the bigger the number gets, it goes to infinity. If you have like a bunch of zeros here, this would have more zeros here. So it would grow closer and closer to infinity. And we're going to test these ideas with what we're going to call asymptotes tomorrow. So I just wanted to, and I didn't really need to do a chart. I was thinking I might need to, but we're going to use these concepts of going to infinity or going to 0 with the asymptotes as we move forward. And these are just boundary lines that will happen with rational functions. These are like, have you ever seen the little dog, usually it's a little dog, in an invisible fence, and they make that path in the yard where they run? You know what I'm talking about? So, if you know what an invisible fence is, where they wear the collar?
Oh, yeah, I know.
Okay, so, and then that dog just runs the fence trying to chase whatever. And so you can see it's no longer invisible because the dog's made a path in the grass. So asymptotes are like boundary lines. You can't see them, but they change how the dog runs through the graph. Okay, they're going to be like our invisible fence lines. I'm not going to put collars on you though, so it'll be okay. So these are our big ideas for tomorrow. These are the problems that I want you to work on, and you've got a couple minutes if you want to at least jot them down. Or you could start on them for tomorrow. I just want you to write the factored form. So this is on page 361. It's in the section we just did, like Jack asked about 37. It's like that problem. There's 3 problems, 39, 40, and 41. I only want the factored form, so you don't need to multiply it out. If you want to check the 2 odd ones, you can multiply it out. But this is in the last section, 4.4. It's on page 361, 39, 40, and 41. So you probably could knock them out right here before the end of class.